Finishing up test 4. And at this point, I'm thinking, who's making these tests so long? Okay. A particle accelerator is 20 kilometers in diameter. There are 4 magnets equally spaced around the ring. Each is 39.2 meters long, and each creates a uniform magnetic field. The magnets are designed to turn a beam of particles so that they remain moving in a circle around the accelerator ring. Assume the particles are protons moving at a certain velocity. How strong must the magnetic field be? If 4 more identical, equally spaced magnets are placed around the ring, how does that change the required magnetic field? Okay, so this is what we have. We have a magnet that's 39.2 meters long. We have a magnet that's 39.2 meters long. We have a magnet that's 39.2 meters long. And we have one final magnet that is 39.2 meters long. So these, is there anything that's going to bend these particles outside of these magnets? No, at least nothing that we are told about. So therefore, all the bending is going to take place inside here. Well, how much does this magnet need to bend? How much does this magnet need to bend the stream of particles? It needs to bend it. Each one needs to bend it 90 degrees. Well, what is 90 degrees as far as a circle is concerned? 90 degrees, basically what it's saying is this. It's saying the angle between this and this is 90 degrees, right? The angle between each of these is 90 degrees. Well, nothing bends it here and nothing bends it here. All the bending takes place right here. So what that really means is, I'm going to go magnify this drawing right now from one of these magnets. What it means is this. What it means is from here, where the particles leave, to here, where the particles enter, this is 90 degrees. Well, what does that mean? Well, what that means is this magnet is the center of a circle, and yeah, I'll leave it at that. Okay, so what that means is this distance here is whatever this angle is, which is 90 degrees, times this distance here, this radius, and what we're looking for is the magnetic field that will create a circle of this radius. Okay, so now we know what the problem is, so let's just go ahead and take a look at what that is. I don't think we don't really need a coordinate system right now, but I'm going to go ahead and draw my coordinate system like that. So, what is this distance? This is just r theta. R theta. Theta here is pi over 2, so it's r pi over 2. And that's this arc length right here. I'm going to cheat a little, and what I'm going to do is I'm going to say this arc length is just this length right here. This, matter of fact, I'm not even going to worry. Just this length right here. If you guys did something more complicated than that, congratulations. That's good. Okay. So I'm going to say this equals our L, our magnet length. Okay. So now, what is this R? This R is 2L over pi. Well, what else is that R? That R is, we are going to go to our equation sheet and we're going to say, okay, this is a charge moving through a region of uniform magnetic field. The radius is given to us as equals mv over b times q. And so this equals mv over bq. Okay. What's the next thing? Oh, so the next step is we're asked to solve for b, so we're just going to once again rearrange this equation for b, and what we have is b equals, all right, mv pi over 2LQ. Does that look about right? mv pi over 2LQ. Yes, it does. And we're done. Now what we need to do is put numbers in. So what are the numbers that we're given? We're given the mass is 1.7 times 10 to the minus 27. We're given the, well, let's see. Let's do things one thing at a time. V is 2.5 times 10 to the 8th. 2.5 times 10 to the 8th. That's meters per second. We are given, what am I looking for? Pi, 3.14. We are given 2L is equal to 39.2, and Q is 1.6 times 10 to the minus 19, right? Am I remembering that correctly? Yes, minus 19 coulombs. Okay, and that's it. There's our number. We're done. So what is this number? Well, I'm going to do this. I'm going to say this 1.6 and 1.7. That's about equal to 1. Let's see, what else can we do here? And we're trying to wait as long as I can to do some other things, but let's see. So let's just go ahead and say this 2.5 divided by 2 is just 1.25. So I get rid of that. What do we have? This is minus 19. So minus 19 and 27. So this is 10 to the minus, it's plus 19. So this is 10 to the minus 8. That takes care of this. And so 10 to the minus 8 to the plus 8, they cancel one another out. So all I have at the moment is left over is 1.25 times 3.14 over 39.2. That looks about right. I have the feeling I've neglected something, but I'm not going to worry about it too much because these are just numbers. All right. So what do we have? We have 1.25 times 3.14 is, what's a quarter of 3.1? 1.8. So this is 3.94. So it's about, yeah, that's right. It's about 3.9 over 39.2. And so that is about equal to 0.1. Yeah, somehow I was not trying to get that number when I made this. I think I was trying for a number of 10. Nah. But anyway, this appears to be the right number as I'm doing this calculation. So I'm going to stick with that. So this is 0.1, and the units end up being in Tesla, and we're done. Okay, so that's the answer to part A. Part B, what happens if you now, instead of having 4 of these, you only have 2 of these? Well, if you only have 2 of them, then what does this end up doing? It means we only need to make 45 degrees for each of these. So now, instead of this angle being pi over 2, it is pi over 4. Well, what is that going to do here? It's going to change this to a 4 instead of a 2, which means this is a 4 instead of a 2, which means our magnetic field, the required magnetic field, is half as strong, which makes sense. If you only need to turn, I shouldn't have erased this. I should have just changed the angle because the magnets are identical, you remember. So this is still 39.2 meters, but now we're only going 45 degrees in that distance. So it makes sense that with the same length, but only half the required angle, that we would only need half the required field. You can also get that just from looking at the radius equation, and you can say, all right, if the radius is, Hmm. Yeah, the radius is twice as big. Okay, so that's all right. So you got to do this. Just do this, and it's fine. Okay, that's it. You're done. Congratulations.